And we design and build these infrastructures such as beautiful Fenway Stadium, highways, bridges, skyscraper type of buildings like Prudential for people, for community. And actually the formal definition of the civil engineering is civil engineers use their knowledge of physics and science to protect the environment and design and build these infrastructures. But the thing is, we have a challenge, we have an enemy, which is earthquakes. These are some earthquake failures. For instance, this picture is from Turkey, which is a building failure. These two are the bridges failure from California and Chile. This is also building failure from China. The most challenging thing about the earthquake is their uncertainties. Do you know when will the earthquake happen? No, right? Do you know what magnitude or exactly where is the earthquake gonna be? No, we don't know answer of these questions. That's why we have to understand fundamentals of earthquakes so that we can design our structures safe and sound against earthquakes. Okay, story part is over. What's the difference? Height. This one is taller, this one is shorter. Actually, there is one more difference you cannot see right now. Let me do this and tell me what you see. What's the difference? Flexible. This one looks more flexible, this one looks stiffer. Or we can say this tall one wants to move slower, this short one wants to move faster. And what we call these movements as a natural frequencies of these structures. I think you all know what the frequency is, right? Frequency is cycles per second. If I start from here, go all the way and come back, this is one cycle, and frequency is how many cycles you can achieve in 1 second. For instance, for this short one, it completes more cycles than this tall structure, right? That's why we call this short structure as a high frequency building, and we call this tall structure as a low frequency building. And every structure has its own natural movement, natural frequency, depending on two things. First one is the mass of the structure, and the another one is the stiffness of the structure, which also depends on design or construction material. For instance, if I change the dimension of this column, floor thickness, beam dimensions, anything related to design, I also change this movement. And for instance, the structure was made by reinforced concrete. Most of the bridges are steel structure. Your home may be wood structures. These construction materials also change the movement of this structure. Nature frequency, it's very important for us to know because we design our structures with a nature frequency so that we can prevent them from the earthquake failure. I'll explain how later, but now I think we can shake the table. I can shake my table with two different ways. First one is gonna be constant frequency motion, what we call is harmonic motion. And this is harmonic motion, and I can control the frequency of the table by using this gray device. Maybe you can see it says 1 Hertz. Now I am shaking my table with 1 Hertz frequency. Another way of shaking is to put a real earthquake, which you also do, and you will see the difference between this constant frequency harmonic motion and real earthquake motion. So, okay, let's see. Now it's 1 Hertz and both structures look safe, right? Let's make it around 2 Hertz. Okay, 2.1 Hertz or 2 Hertz. Now the taller one is getting crazy. It's like dancing, right? But the people living in the short one, they are safe. They don't feel the earthquake as much as people living in a tall structure for this frequency. Okay, you can think like this. Now I am giving a music to my table and tall one likes it and started dancing, okay? But the short one doesn't like the music that I am giving right now. Let me change the music. Let me increase the tempo. Let's make the frequency around 3.2. Now, short one is started liking my music and started dancing, but the tall one looks safe compared to the short structure, right? Okay, let me stop it and explain what happened here. Actually, the question that I asked, which one is gonna collapse, the answer should be, it depends. It depends on the table frequency that I put. First, I started with 1 Hertz frequency and both structures were safe. I increased the frequency to 2 Hertz. Tall one was getting crazy. I kept increasing the frequency to 3 Hertz. Short one was getting crazy. Do you remember when we were talking about these nature frequencies, natural movements? What did we say about this tall one? Is it a low frequency building or high frequency building? Low. And we said the short one is a high frequency building. I didn't tell the nature frequency of this tall one is very close to 2 Hz, and also I didn't tell the nature frequency of this short one is very close to 3 Hz. So when the table frequency got close to natural frequencies of the structures, something is happening. They are getting crazy. And what we call this situation as a resonance. Have you ever heard resonance before? It's very dangerous in terms of civil engineering point of view. We don't want to get into resonance. That's why we design our structures with a natural movement, with a nature frequency far away from the earthquake frequency, so that they will not get crazy during the earthquake. This is basically simply how we design our structures against earthquakes. Now I think I can shake my table with a real earthquake. Let me turn the machine on again. I'll put this earthquake, which was recorded in California, 1994 Northridge earthquake. The magnitude was 6.9, which is actually a huge earthquake. And this plot shows the y-axis is horizontal acceleration versus time. This is not a magnitude time plot. This is a horizontal acceleration versus time plot. This earthquake happened in California has mostly higher frequencies. So, what do you think? Which one is gonna collapse? What's the difference between this real earthquake shaking and the previous one, besides collapsing the short structure? What was the difference? Yes, real earthquakes have different bunch of frequencies. Sometimes my table went faster, sometimes it went slower, right? Okay, another question comes up then. What earthquake frequency do I need to consider before I start designing my structure? Because, as I said, I can control the natural movement, nature frequency of the structure by changing its mass, design, or construction material. I have a control on that. But the earthquake frequency is some other nature. So how do I know the earthquake frequency that I need to consider for my design so that I can arrange my nature frequency far away from the earthquake frequency? Yes, we are looking at the past earthquakes data. For instance, how did I say this earthquake happened in California has mostly higher frequencies? Because the behavior of the earthquakes happened in California. We have collected a lot of earthquake data, and we know the earthquakes are higher frequencies in the California, west coast of United States. And there's a lot of seismic recording stations around all over the world. Actually, we have also one seismometer in the Northeastern Universe, and we can catch the earthquakes all over the world if their magnitudes are larger than 6.5. You can just see the 2 screens in front of the elevator when you get out of the laboratory. You can check it. So my point is there's a lot of seismic recording stations around the world, and they are recording the earthquake data continuously. And they come up with a term which is predominant earthquake frequency for a particular region. So we can design our structures with a nature frequency far away from this defined predominant earthquake frequencies for a particular region so that our structures will not get crazy during the earthquakes. This is how we design our structures against earthquakes. So I want to shake my table one more time with the same earthquake, but this time I want to improve my design for this short structure. Maybe I can prevent it from the failure. So do you have any suggestions? How can I improve my design for this short structure so that it will survive against the same earthquake? Yeah, just
add like a crossbar like between them.
Yes, this is exactly what I'm going to do. I'm going to add these diagonals like this, and let me explain how this works against the earthquakes instead of explaining in a way of nature frequency. I think you all know the famous physician Isaac Newton, right? And there's a famous equation he derived from, which is force is equal to mass times acceleration. This structure has its own mass, and when the earthquake hits, there's an acceleration on my structure. So therefore, there should be horizontal forces acting on my structure during the earthquake. Let's think about the horizontal force acting here. Now this force should be transferred from here to the foundation in order to decrease deformations, and half of it is going to go through this column, beam, and column to the foundation. But what if I put this diagonal here? Now I am dividing my force into 3 instead of 2, and also I open the knee pad for the force transferring from here to the foundation. And actually I also changed the nature frequency of the structure. Let me turn the machine on. I'll put the same earthquake. Let's see how these diagonals work against and how these diagonals help my structure. And the reason why I put the diagonals in this direction, because for my shake table, horizontal forces acting on my structure is in the direction of the movement, in the direction of the acceleration. That's why I put the diagonals like this. If I put like this, they will not work out for my earthquakes. And there are also some other ways to improve design against earthquakes. For instance, what Japanese people do is they put some rollers on the foundation and they decrease the deformations with the help of these rollers.